Ever wondered how to make smart decisions when the future is full of uncertainty? Imagine you're an investor trying to grow your money in the stock market. You don't know the exact drift, the average return of the assets you're investing in. You might start with a guess or a prior about how the market will behave. But what if that guess is wrong? Traditional methods can fail badly in that case. Today, we're diving into a groundbreaking approach that helps make decisions more robust, even when your initial assumptions are shaky. Let's break it down. In classical Bayesian control, you use a prior belief about unknown factors, like the stock's drift, and update it as you gather data. This works great if your initial guess is spot on. But in reality, priors are often flawed. That's where Distributionally Robust Bayesian Control, DRBC, comes in. Here's the twist. Instead of trusting your prior, you imagine a worst-case scenario, adversary. This adversary picks a slightly different prior, within a mathematical divergence neighborhood of your original one. Think of it like stress testing your strategy. By preparing for the worst within a reasonable range, you avoid overconfidence while staying resilient. The key innovation: a mathematical technique called strong duality, which connects this adversarial game to concepts in financial mathematics. This lets researchers translate the problem into a form that's easier to solve. They then use advanced tools like neural networks to train policies, essentially decision-making rules that adapt to uncertainty. But how does this work in practice? Suppose you're managing a portfolio. The DRBC method doesn't just rely on your initial guess about market trends. It considers a range of plausible scenarios, adjusting your strategy to handle the most challenging ones. This reduces the risk of being blindsided by unexpected events. The paper also introduces a new algorithm, leveraging randomized multi-level Monte Carlo estimation, to evaluate these policies efficiently. They even show that, in specific cases like the Kullback-Leibler divergence, a way to measure how one probability distribution differs from another, the math simplifies beautifully, making the approach practical. What's the takeaway? By blending Bayesian reasoning with adversarial thinking, DRBC offers a smarter way to navigate uncertainty. It's not about being overly cautious. It's about building strategies that hold up even when your assumptions aren't perfect. Now let's zoom out. Ever wonder how scientists predict the future when the world is full of surprises? Today, we're exploring a mind-bending blend of math and real-world problem-solving that helps us navigate uncertainty. From stock markets to physics, these ideas are shaping how we make decisions when the path ahead isn't clear. Imagine you're watching a tiny particle floating in water. It's jiggling around randomly. This is what mathematicians call Brownian motion. It's not chaos, though. It's a pattern hidden in randomness. Now picture this. Instead of a particle, you're tracking a stock's price. Those random jitters, they're the same mathematical beast. But how do you make sense of it? Here's where things get clever. Researchers use conditional expectations, a way to update predictions as new information arrives. Think of it like checking your weather app. When clouds roll in, you adjust your forecast. In math terms, this means refining estimates based on the latest data. It's how we turn uncertainty into something manageable. But there's a trick to make this even more powerful. By redefining the rules of the game, essentially creating a new probability measure, let's call it P. They show that some processes, like Brownian motion itself, behave independently of other factors. It's like recalibrating a scale to weigh things differently, yet still trust the results. This independence is a game changer for simplifying complex systems. Now let's talk about Ito's lemma, a mathematical superhero for dealing with random processes. Imagine a pendulum swinging. A tiny nudge can send it into a wild swing. Similarly, small random fluctuations in markets can have big impacts. Ito's lemma helps us calculate how these tiny changes affect related quantities, like the value of a financial option. It's the math behind fair betting systems and the backbone of modern finance. But how do you turn all this into a decision-making tool? Enter the martingale, a process where the best guess for the future is today's value. It's like a fair game where no one has an edge. Researchers use this to model optimal strategies, balancing risk and reward. Think of it as finding the perfect chess move when you don't know your opponent's next play. Why does this matter? These concepts aren't just for textbooks. They're the invisible engine behind financial models, physics simulations, and even AI. When you're investing, designing a bridge, or training a machine learning algorithm, you're relying on these ideas to handle the unknown. The math might look intimidating, but it's all about making smarter choices when the future is a mystery. So next time you hear terms like Brownian motion or martingales, remember, they're not just abstract theories. They're the tools that help us navigate a world full of uncertainty. And with methods like DRBC, we're not just reacting to chaos, we're building resilience against it.